Good evening, everybody. I'm sorry that today didn't work out in terms of me getting back in time for class for my doctor's appointment. So I've made this video for you, which will certainly not replace our time in class, but hopefully be a good substitute under the conditions that we were in. You should find that the lesson I'm going to go over really is just a natural extension of what we did in class on Tuesday. Remember that on Tuesday we looked at polynomials, and today we're going to look, instead of polynomials, at rational functions and inequalities. Okay, you're going to find that the process is really the same, but because they're rational functions, which is really just kind of that fancy name for a fraction, we've got to take account for that denominator as well. Okay, so in this first example, we have f of x equals x plus 8 over 4x squared minus 8x minus 5. And in the denominator, that 4x squared minus 8x minus 5, let's go ahead and factor that. And that's going to factor into the quantity 2x plus 1 times the quantity 2x minus 5. Okay. So the first question that we're asked about this rational function is to find its denominator. Not its denominator, its domain. Okay? The domain and the denominator are related though, so I apologize for my mistake. When we are asked to find the domain of a rational function, remember that in domain we can't have a 0 in the bottom of a fraction. Our denominator cannot equal 0. Okay. So, that being said, in the particular rational function we have in this example, we're going to have an issue in the domain when 2x plus 1 equals 0 and when 2x minus 5 equals 0, because those were both the factors in our denominator. If we solve 2x plus 1 equals 0, we're going to find that x equals negative 1/2. And if we solve 2x minus 5 equals 0, we're going to find that x equals 5/2. Okay? Those are two numbers that we cannot have in the denominator of our fraction. Therefore, they are not in our domain. Every other number works except for negative 1/2 and 5/2. So when we go to write this domain in interval notation, we're going to start at negative infinity. We're going to go up to negative 1/2, but it's not included, so it gets a parenthesis. We're going to union that, pick up on the other side of negative 1/2, go all the way up to 5/2, but again we're going to use a parenthesis because it's not included, and then union, pick up on the other side of 5/2, and go all the way to infinity. Okay, so that's our domain for our rational function. Okay, the next part asks us for the y-intercept. Okay, now remember that when we talk about y-intercept, or remember it's also called the vertical intercept, it's got to be a point. We're looking for 0, comma, some number. Okay, and remember, to find the y-intercept or the vertical intercept, we need to plug in 0 for x. So, in our case, we're going to have 0 plus 8 in the numerator over 2 times 0 plus 1, let me throw that in parentheses, times the quantity 2 times 0 minus 5. Alright, so in my numerator, 0 plus 8 is 8. Then in the denominator, I've got 2 times 0, which is 0, plus 1. 0 plus 1 gives me 1. And I have 2 times 0, which is 0, minus 5. And 0 minus 5 gives me negative 5. So this leaves me with 8 over negative 5. Okay. That's not my answer, though, because remember, y-intercept always has to be written as a point. So my point is 0, comma, 8 over negative 5. Okay. Now we need to look at the x-intercept. Okay. Remember, the x-intercept, also a point, is going to come in the flavor of a number, comma, 0. Okay. And we find it by setting the equation equal to 0. So we need to set x plus 8 over the quantity 2x plus 1 times the quantity 2x minus 5 equal to 0. Excuse me. Now, what's kind of cool about when we solve a rational function equal to 0 is if we want to get rid of our fraction, we need to multiply both sides by our denominator. If we multiply both sides of our equation by the denominator, 0 times whatever the denominator is still going to be 0. So that being said, when we're solving for the x-intercept, really all we need to pay attention to is when the numerator equals 0. So we care about when x plus 8 equals 0, and that's going to happen when x is negative 8. Okay? But our point is negative 8 comma 0. Our x-intercept has to be a point, remember. Okay, the very last question on this slide asks me for the vertical asymptotes. Okay, the vertical asymptotes in the domain, let me get a better color than that. The vertical asymptotes in the domain are very closely related. Okay, vertical asymptotes occur when my rational function is undefined. They occur when the denominator is equal to 0. And they will always come in the flavor of x equals some number. Okay, so let's make ourselves a little note here where denominator equals 0. Well, we already found out in the first part that the denominator equals 0 when x is negative 1/2 and when x is 5/2. So those are also our vertical asymptotes. So our vertical asymptotes happen when x equals negative 1/2 and x equals 5/2. All right, now in this slide, my goal is to show you visually what vertical asymptotes look like. So in the previous slide, we talked about algebraically, those vertical asymptotes happen when my denominator equals 0. Okay? Visually, in a graph, you're going to find that vertical asymptotes are that line straight up and down. They're vertical, okay, in which the graph gets closer and closer and closer to that point, but it never actually touches it. Okay. In this particular slide, you're going to see your vertical asymptotes represented by those dotted red lines. Okay. Now remember that vertical asymptotes always come in the form x equals some number. So in this particular slide, our vertical asymptotes are going to be x equals negative 3 and x equals 4. Okay, same graph where we just figured out our vertical asymptotes. We're at x equals negative 3 and x equals 4. Now we want to talk about where is this function positive, where is it negative, where is it 0, and where does it not exist. Okay, so remember that when a function is positive greater than 0, it means that it's going to be above my x-axis. Okay, that's just like it was on Tuesday. If it's negative, less than 0, it's going to be below my x-axis. Okay? If it's 0, equal to 0, it's going to be right smack dab on that x-axis. Okay? And when it does not exist, that's where we're looking for those vertical asymptotes. All right, so let's make ourselves a couple little notes here. Positive means above x-axis. Negative means below x-axis. 0 means on x-axis. And when it does not exist, we're looking for vertical asymptotes. Okay, so in this particular graph, it is above my x-axis from negative 3 to positive 3. And then again, from 4 to infinity. All right, now we're looking below the x-axis. We're looking where it's negative now. So we're talking negative infinity to negative 3. And then we're talking from 3 to 4. Okay. So negative infinity to negative 3, union 3 to 4. Okay. Now, it's 0. It's on the x-axis right at that point of 3 itself. Okay, so it's on my x-axis at x equals 3. Okay. Now, it does not exist at my vertical asymptotes, and we already said in the previous slide that those vertical asymptotes happen at x equals negative 3 and x equals 4.